a lot, Manuel, for the introduction, and good morning, everyone. So we continue our lectures on toric varieties, and we are following the notes of David Cox, which, again, you can find online from his website. Today, our goal is to discuss the relation between toric varieties and polytopes. So we are going to fix a lattice n, which is just isomorphic to Zn, and continuing with the same notation as before, the dual we call M, and that one is also then isomorphic to Zn. By dual, we mean home to Z. So we have two copies of Zn that are dual to each other, and previously we defined these polytopes, which are the convex hull of finitely many points. So let me draw something like this. You are given finitely many points in Rn, and then you take the combinations. If your points are the pi's, we take the combinations sum of lambda I pi, where your lambda i's are all greater or equal than 0, and these guys are going to be the sum of the lambda i's is 1. So we take those combinations. We move this down here, and we get the convex hull of those points. And now we are going to add an additional condition. Since we don't have just a copy of Rn, but inside that Rn we have a distinguished Zn. Oops, somebody called Luis. Okay, so then we have over here, we are going to consider those where the points that we are going to take convex hull of come from our lattice, and then we are going to call those lattice polytopes. So a lattice polytope is the convex hull of a finite set of points, but they have integral coordinates. And during the lecture, we will assume that P has dimension n. The polytope, like if this lives in R2, is 2-dimensional. Lives in Rn is n-dimensional. We have the definition of a cone from before. For a cone, the definition of a face was that we have one of these hyperplanes. You have dot product with something, so that this vector, say u, does dot product with all elements of the cone greater or equal than 0. So it gives me a half space, a closed half space, where my cone lives, and the face is the intersection of that boundary with the cone. The face is the intersection of the cone with the boundary. The definition for the face of a polytope will be the same. So for the polytope that I drew over here, what would be a face is the things that you would imagine, possibly you would imagine, that are a face. So let me draw a line over here, and I'm going to use that line to define some face. So I move it so that it satisfies the condition. All the polytope is on a side, and the intersection is the face. So this is defining this point as a face of that polytope. Well, I guess if I put it over here, oops, if I put it like, that's not the one that moves things. This is the one that moves things. If I put it over here, I guess the whole thing is a face. The whole polytope is a face of itself. The vertices are faces, and as one would like, one like this would define this guy over here as a face as well. Very good. Essentially the same definition that we gave for faces of a cone. Now, a facet, the same situation as over there, is going to be a face of dimension 1 less than the total dimension. So we say codimension 1. A vertex, as one would imagine, is just a face of dimension 0. In my example from above here, 5 vertices. And by our assumption that we are taking a lattice polytope, one can see that the vertices are a subset of the points that I started from taking a convex hull. I could have taken extra ones inside, which do not affect the final answer. So not all of them make it to be vertices, but in any event, the set of vertices is a subset of the original ones. So in a lattice polytope, the vertices are lattice points. Lattice points, again, are the ones in our distinguished lattice that one time is M. When we are in the dual space Rn is N. In this case, we are putting, like these polytopes, in the Rn where M lives. Okay, what else are we going to say? The assumption from before that P has dimension n means that if we look at the normal vectors of the facets, those are unique up to multiplication by a non-zero real number. Yes, that makes sense, because those facets are dimension n minus 1. So if you look at the linear span of that, like you pretend that the origin is a point inside that and take the linear span from there, like if that was the origin, you get a dimension n minus 1 linear space. And then over there you can see that there will be a one-dimensional complement of that one with respect to the whole thing. So what we are saying is that in this case that it is R2, if we look at the faces of size 1, the perpendiculars to all of those, let me draw a perpendicular to one of those over here, the normal directions, a normal vector is unique up to multiplication by a scalar. But now we have the extra data of being a lattice polytope. So I can solve things over Qn, and then that tells me that I can choose this guy with rational coordinates with respect to the lattice. And then even more so, I can stretch it or contract it as I like to make it integral coordinates. And if in addition to now make it integral coordinates, I choose it pointing inward, then now it is unique. What I'm saying is for each facet of a lattice polytope, we can get this one over here. It is the very first integral point along this. And again, we know there are integral points just by using some linear algebra over the rationals, using that our starting place was points with integral coordinates. Then very good. We are going to be using these guys along the way, those inner pointing normals that are the very first one on that perp. Okay. And we are going to even have a name for those. If you have one of these codimension 1 faces, meaning facets, and you call it F, we are going to consistently write n sub F for this guy over here. So with some purple color, if this one in purple is F, this vector over here is n sub F. Not in that position, we don't really care about that, but it's just that vector that I can take anywhere we like. Very good. Now this is the following situation. Then notice that from our previous conversation, we have at least 2 ways to define our lattice polytope. One way was that we start from finitely many points with integral coordinates and we take a convex hull, but notice that we also can do intersection of half spaces. How is that? Like the picture from before, somewhat. And then what you would be intersecting would be, this is like one of the half spaces. So I'm going to move that one a little bit over here. The half space that that one defines would look somewhat like this. Take me a century to color it properly, but I'm going to kind of do some type of coloring over here. Anyway, so there is the half space that I get from that one. And then it doesn't take too long to convince yourself that if we do this for every facet, we recover the polytope. So we are going to use those 2 descriptions. We have one that is the convex hull of those vertices or whatever points we started from that are lattice points. And we also have this nice one that would be intersection of some half spaces. And by that we just mean that do the same for the other facet as well and intersect all of these, and you can see that we get back our polytope. But then let's think for a second what data we got over here. From that half space, there is this boundary here that is defined precisely by our NF. That one is perp to our NF. Let me do that guy over here. I guess you can imagine this perp is not too perpendicular over there, but I guess it's okay. So, perpendicular enough. So, we have our NF over here. So, that particular supporting hyperplane over there, like this one that supports this facet and has the polytope on one side, is defined by dot product with NF equal to a fixed quantity. Then it can be written like this. It is this line over here that I can color in, well, it's already a nice color, but maybe to distinguish it even more, I'm going to change it to red. That red one is defined by something like this. Then, if we let this run over the facets, we have this presentation for our polytope. It is the intersection over the facets of a dot product with each of the corresponding NFs greater or equal than some quantity. And you might wonder, why would these guys want to put a minus there? The reason to put a minus there is that it doesn't show up in some other place where one uses it a lot. There is some other place where that AF shows up, and one doesn't want the minus over there, so the price to pay is to put it here. Is to have some formulas be clean later on. Then now we are going to do the following. Given a polytope, given a lattice polytope, we are going to get a fan out of it. What was a fan again? Was a collection of rational polyhedral strongly convex cones that fit nicely, meaning close undertaking face, and any two of them intersect on a face. Out of each of those cones, we got an affine toric variety, and we use the data of the fan, how they fit together, to glue them. That gave us a toric variety, and the important thing is that every toric variety that is normal arises this way. Okay, we are going to get a fan out of a polytope P. How would that be? For any face of the polytope, notice that we are using a different font to distinguish it from the facet that we are calling like normal font F. This is like fancy font F. Given any face F, not necessarily one of the uppercases with normal font F, we are going to construct a cone. But this cone doesn't live where the polytope lives. The polytope lives in the one that we are calling M. This sigma that we are associating to fancy F lives in the dual one, lives in the one that we are denoting N. And it is the cone generated by all NFs, by all facet normals, as you let the facets run over the ones that contain your fancy F. There was a lot that we said over there. Let's work out one example to see what we just said. But before I go to the example, let me just tell you one thing. One can see that each of those guys is strongly convex rational polyhedral. It's a cone that is strongly convex rational polyhedral, and one can check that those guys together fit nicely. It's close undertaking a face, and any two of them intersect on a face of both. It's a fan. People call it the normal fan of the polytope. Then now we have a way to get a variety, a toric variety. Start from your polytope, run this procedure, we will do an example in a second, run this procedure to get a collection of cones. Turns out they fit nicely, give you a fan, and out of that fan you get a toric variety. We are going to denote it like X sub P. P must show up in the notation because it is coming from P. P gives you a fan, P living in MR, gives you a fan in NR, and out of a fan, we have discussed how to get a toric variety. Then let's do an example over here. The example is that we are going to take the unit square. In the case of the unit square, which is drawn over here, the vertices are 0, 0, 1, 0, 1, 1, 0, 1. That's one of the possible representations, is the convex hull of those four guys. But also, we said that we have the other representation, intersection of some half spaces, intersection of some closed half spaces. Then one can see that we get the inner pointing normals giving us those. So for example, this would be dot product with 1, 0. Will be dot product with a guy like this. That would say that, no, never mind, with this guy, I guess. Never mind, yes, it's this guy. With 1, 0. I said 1, 0, but I pointed at 0, 1. No, it's 1, 0, the one that I want. If I do dot product with 1, 0 on the vector AB, I get A. And in this case, it's meant to be greater or equal than this one, greater or equal than 0. Because it's precisely the dot product that you need to define this one. So that's why it's A greater or equal than 0. And similarly for the other ones, you see B greater or equal than 0 would be this half space here. So yes, it is contained there. Minus A, this would be A smaller or equal than minus 1. So it's this part here. And the last one is B smaller or equal than 1. So it's this one here. And if you intersect those four, you get the polytope. So we have the presentation. The inner pointing normals are these guys. So what is the construction of the normal fan that we just mentioned in the previous slide? Let's do the construction. It says you do something for every single face of your polytope. There is a procedure that you are going to do for every single face of the polytope. So let's pick one. Let's pick, for example, 1, 1, which is a face of the polytope. What it says is that you look at which facets contain it. There is one over here, and there is one over here, two facets containing it. Then it says, for each of those, look at the corresponding perpendicular, inner pointing perpendicular. So for the green one is this one, for the yellow one is this one. So we are working with this guy. Yes?
You also have yellow there.
Oh, that is very good point. Like, let me change my colors here.
Green in my computer.
Yes, I'm going to change one of the two. I'm going to change it to, maybe this is different now. Very good. Thank you for pointing that out. Thank you for pointing this out. Yeah, like, I had also some figures that do a color and do different colors over there. This is very interesting. Okay. Then, and I'm not going to call it, is that purple? Because here is purple. Is that pink over there or purple? Well, that one that might be pink or purple is over here. This is the purple, this is the NF of that one. And for the one that I believe is yellow, you have this purple over here. So for this phase, again, it's a procedure that we do phase by phase. We get a cone that is the cone generated by these two. You see, for that phase is the cone generated by these two. So is the one that you see in the picture below. Let me change color so that, because now I know that the other one doesn't work, it will be this cone. You see? We did it for this one, we go this orange one. But we can do it for this vertex, for this vertex, for this vertex. We also do it for this one. Let's do it, for example, for this one. So let me erase a little bit. Maybe it's good to keep it, but I'm going to do it on a different copy of this guy done maybe over here. I'm working on that side up there. I have this square, and we are going to work with this particular one. This is already a facet. So I ask myself, what is the collection of all facets containing that facet? Well, only one. Yes, exactly. And then now we look at the perp, only this one. So what I get, the contribution to the fan that we are creating would be the cone spanned by this guy. So it would be this one. So this is the contribution. If I call this phase like F sub 1, and this is NF sub 1, that's contributing this sigma sub 1. And if we call this vertex, say, phase number 2, the contribution is this sigma 2. Each face of our polytope is contributing a cone in NR, and you put all of those together. One can see that in this case, you could say maybe by symmetry, from the picture one can extrapolate and see that what we get as a final result is this one. The cones are like this. The maximal ones are these four. And then the faces of those. So this ray would be there, 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 and the origin coming from using the whole P. The whole P is in no facet, so on the other end I get the span of nothing, which is 0. And then we have seen this one in several examples. That's the one that gives you as a variety P2. Then we see over here, okay, so if you use the unit square, the toric variety that you get out of the unit square is just P2. I'm saying, I didn't see it written. I see it. It's just because I'm thinking of the next slide, I'm going to do P2. Thanks a lot. Thanks a lot. Yeah, like, sorry. Okay, thank you. Yeah, because I'm going to do P2 in this one. Thank you. Okay, so notice the following. With this construction, polytopes that are equal up to scaling give you the same normal fan and hence the same toric variety. So let's see that. So if I do this one over here, so I want to do, say, let me see if I can draw this. I should have closed it. Pretend that that's 45 degrees. Okay, so say that we start from this one, and let's do the construction. So the construction uses the NFs, right? So I'm going to draw some NFs over here for those guys. And then suppose that I have a friend that doesn't like that one over there, oops, and likes it in a different position. Then what does the friend get when they do the construction? You see, they get exactly the same. So if you use the corresponding, if you use this vertex, and my friend uses the corresponding one in the translation, well, there is two statements here. I'm focusing the second one first. Translation. If I translate it and use the corresponding translated face, you get the exact same thing. You can see because the NFs are just the same, the exact same thing for the second one. And if yet another friend likes to scale this one, and this friend works over here, well, one thing that could have happened to the friend is they just scale these NF guys, but they scale them back. They have not really changed direction, so they are just the same when you scale them back to be the correct, going from the lattice point up to the lattice point, like going between lattice points, like the first one in the perp. Then you see again, you get the exact same normal fan. And in this particular case, for all of those, would be a normal fan looking like this. So those perps, if you do it for the vertices, it would be the cones generated by pairs of these guys. So I need to draw those three anyway. So I'm going to get one guy like this. I did it the way that I didn't want. Anyway, too late. Then there will be this guy, there will be this guy, and there will be this guy. So then one can see that is up to a rotation, the same one for P2. When you do it for the facets, you get only these three guys. If I wanted to get the version of P2 that we have been doing, what I should have done was like this, like 45 degrees here, and this one, and this one. Let me make this green. And this one is the one that would give me the P2 that we were drawing before. that one would give us, when you do it for the facets, you would get this one. For the other facet, you get this one. For the other facet, you get this one. And when you do it for the vertices, you get this guy, not that one, this one, and this one. And when you do it for the whole thing, you get the zero cone. Very good. So now, why are we looking at this type of fans? Why are we looking at the fans that arise from polytopes? So the answer is that those ones correspond to projective toric varieties. So remember, we have normal as an assumption in our toric varieties. The toric variety of a fan is projective if and only if the fan arises from some lattice polytope in that way. So if we want to get projective toric varieties, then it's really easy because you just start from a polytope and get the fan from that and get your variety. And a way to check or not if it is projective, well, you have to do some computations, but it will be to try to find a way to check that. Very good. Turns out, from the construction, one sees that the polytope is combinatorially dual to the normal fan. What are we meaning by that? A correspondence. So there is a one-to-one inclusion reversing correspondence, inclusion reversing, I mean, between the cones and these faces. That was from the construction, and one can do a computation and see that one sees that it's inclusion reversing just from the definition, and what requires maybe just a small moment of thought is that this is what is going to happen. The dimension of the face of the polytope F that you start from is related to the dimension of the cone that you get out of it in the way that they add to n. They add to the size of the vector space where we are working. And remember, we assume that our polytope P has size n. Then combining this with the correspondence between cones and torus orbits, then now we can write the correspondence between those three things. So we get a one-to-one dimension preserving correspondence, dimension preserving because we are using two dimension reversing ones out of a certain one. So it becomes dimension preserving when we look at the faces of P and torus orbits. So the whole P would be the whole variety, the invariant points would be the vertices, and so on. Then let's write down some of that. The vertices correspond to n-dimensional cones of your fan and correspond to fixed points of the torus action. The facets of P, so faces of dimension 1 less than the whole P, in this case dimension n minus 1, correspond to the rays in the fan, because that one is inclusion reversing, but then we do another inclusion reversing correspondence, and then we get now inclusion, I meant to say dimension, like they add to n, and now we are using one that also adds to n, so I get back the same number, correspond to torus invariant irreducible divisors. These are size n minus 1, so these are size n minus 1. Irreducible varieties of size n minus 1, those are the ones that we are calling irreducible divisors. And in general, P determines the combinatorics of the toric variety. So yes, P determines the whole toric variety, so then in particular determining like all that you can get out of it. Something that is helpful is to define this polar polytope. If we have a P that contains the origin as an interior point, and you are like, oh, mine doesn't. Oh, but remember that you have this option to translate without affecting the toric variety that you get at the end. So if it doesn't contain the origin, just go ahead and translate it so that it contains the origin, and you can define this other polytope called the polar polytope. Some people call it the dual polytope, defined as follows. This one P lived in M. P, this polar, lives in N. And is defined as follows. Is the set of the U's that do dot product at least -1 with the points of your polytope. And then one can show that the following happens. We'll see an example in a second. If this happens, first of all, that P0 contains the origin in the interior, is not hard to see why, like you have that 0 satisfies this. And then one can see that there is a little bit of wiggle room because 0 satisfies this with equality to 0. So you have a little bit of option to move in all directions over there. So one sees that this is indeed true. And then the vertices of this one would not necessarily be lattice, it would just be rational multiples of lattice. Okay. And there is a type over here. This should be an N. All right. Now you know. Let me fix it over here. This should be an N. Okay. It doesn't need to be a lattice polytope, so let's see an example. If we start with this one up here, that if I draw it, there is 1, 2, 1, 2, 1, 2, 1, 2. So one vertex is over here, one vertex is over here, one vertex is up here, and one vertex is up here. So it is this one. This is our starting P. This one is P dual. And we know the fan that we get out of this guy, right? We did it a moment ago. We get the normal fan out of that guy. These are the two-dimensional cones in it. And the maximal cones determine the rest because it's now faces of all of those. Okay. This is one of the uses of that polar polytope. It is not a lattice polytope, but at least allows us to do the following. One can show that the normal fan that you get out of P, so the one that we have been talking about, you can obtain easily from this like dual one, from the polar, by taking the cones over the faces. It clarifies here that is relative to the origin. What do we mean over there? That, for example, let me paint this one in red. So you take all like the cone generated by that. So this is one of the cones. So this one here is one of the cones. And similarly for the other ones. So for this one over here, I get this one, and for this one over here, I get this one, and for this one over here, for this one, you get this. So what this is saying is that what we are observing in this case, what we are observing for this particular polytope, that we passed to the polar P, this one here in the center, this one here in the center, was this P0 for each of the faces. We look at the directions from 0, well, the proper faces, and it should say proper faces. Anyway, taking cones over the proper faces, I guess. Yeah, proper faces here. I don't use the whole thing. Then you recover your fan. Very good. Then now, the example over here is what we just did. That out of this P, we get this fan of P1 cross P1, and we can see that we recover it easily from the polar polytope. And in this example, as is pointed out here, it is not a lattice polytope. It's not true in general. Very good. So now, let's say a little bit about one of the uses of these polytopes. There is this notion that I will somewhat review of an ample divisor. It's one of the uses of these ample divisors in algebraic geometry and commutative algebra. Suppose that we have a polytope, and as we said, it's n-dimensional, and we are assuming today that they are lattice polytopes. The facet normals determine the fan, and that gives us the toric variety. Very good, but there is more data than just the facet normals. There is also what dot product you get with the facet. So this here does change if I translate. So the NFs don't change if I translate, or if I scale. The NFs stay the same, but these AFs for sure change. If I translate, these AFs change. If I scale, this AF change as well. Is no problem at all. But we want to study those guys. What is the meaning of those guys? So I can take those AFs. Each AF is associated to some F facet, and we said before the facets correspond to irreducible divisors. So I can define this. I can produce a divisor by simply using those AFs as coefficients. So what's going on over there? We'll do a concrete example in a second. We have one guy like this. So in our toric variety, say that here we have 5 facets: F1, F2, F3, F4, and F5. Each one of those corresponds, say that I have the variety, I'm going to draw it like this, a cartoon, say that you have X, and out of each of those guys, out of each those FIs, we get some, say, F1, say F sub 2, I'm just drawing a cartoon, F3, no, not Fs, these. Yeah, right? I want to just write the divisors. So say D1, D2, this is just a cartoon, D3, D4, D5, and then each of these ones comes with some number attached. This, say for example, is the points that have dot product with NF equal to minus AF. Say dot product with NF1 equal to this number. Then what we do, and let me the F's over there, say that we call these ones N1, N2. I went the wrong way. Okay, let me go the right way. N2, N3, and N4. So the dot product with this N1, say, is A1. So what this procedure is saying is form the divisor D equals to plus in this case, equals to A1 D1 plus A2 D2 plus A3 D3. Is this going to fit there? A4 D4. I think I can do it. Plus A5 D5. It's not readable, but I did it. Anyway. So then, what this is saying, it depends on the position and the size of the polytope. Out of the polytope, we are getting a formal combination of codimension 1 subvarieties. And I could go back, you see, because if you give me one of these, I just attach, I just do half spaces that are dot product with the corresponding Ni for these guys, dot product equal an inequality with respect to minus Ai. Those give me some half spaces, and I can, well, with some assumptions, I can recover the polytope. And we are going to see some of that just now. So if you have positive, this is an example, positive integers R and S. So we are considering a rectangle that is along the axis length R, along the x-axis, and along the y-axis is length S. Okay, it doesn't hurt if we draw a copy over here. Okay, there's our rectangle. So what do we expect? I guess we expect a P1 cross P1 over there. Okay. Then the facet normals are these guys, like N1, N2, minus E1, E2, minus E1, and minus E2. So then the normal fan is something we have seen before, would give us P1 cross P1. And now let's see, to digest a little bit, the recipe to get our divisor out of this polytope. How do we get the divisor? Well, there are 4 irreducible divisors corresponding to these guys. To N1, we have a D1. To N2, we have a D2. To N3, we have a D3. To N4, we have a D4. And these 4 numbers, it's a bad choice of color because there is already something with that color, but I can fix it. Okay? So those 4 minus those numbers are the coefficients that we use on these guys. I can move it, this one will go here, one will go here. So 0 is the coefficient of this guy, 0 is the coefficient of this guy, minus r, so r is the coefficient of this guy, minus s is the coefficient of this guy, so it is written here. That's the recipe. You go over the facets of the polytope, those correspond to the invariant divisors, and then out of the particular position, it is dot product with a particular number, so minus that number is the coefficient that goes in the irreducible divisor, and I get this thing. Okay. This divisor has very important properties. I don't know how easy is really this one, but it's easier than some other ones, so let's call it easy, that it is a Cartier divisor. Then let me say one quick word about what that means. Cartier divisor, in the normal case, you can think of these guys as the veil divisors, the one from before, just a formal combination of irreducible divisors, again, formal codimension of subvarieties of codimension 1, but that locally over some cover are div of some f. That is a Cartier divisor. Locally is principal. So let's see, that's what this slide says, but then let's go over it. We are going to restrict this treatment to normal varieties. One can still define these ones when the variety is not normal. Well, now one would need a little bit more work. But in normal varieties, the Cartier divisors inject on veil, so I can just give this presentation over here. So if you have a veil divisor on a normal variety, and what is the restriction of the divisor to an open set U, to an empty open set? What you do is the following. Basically intersect, like your D is a sum with coefficients of some DIs. Some DIs might miss your U, and some other ones intersect your U. So this is X, this is our U, and our divisor can be 3 times this one, plus, say, 5 times this one, minus 7 times this one, and, say, plus 12 times this one, and minus 15 times this one. Say that that's the divisor. 3 times this one, plus 5 times this one, minus 7 times this one, and plus 12 times this one, minus 15 times this one. How do I restrict to U? This I ignore. I don't need them anymore because they do not intersect U. And the divisor that you would get as the restriction would be now U intersected this guy with the same coefficient. U intersected this guy with the same coefficient, and U intersected this guy with the same coefficient. That's what this formula says. Only take the components, the irreducible divisors in your formal sum that intersect U, and use the exact same coefficient. And to get irreducible divisors on U, just intersect with U. Like this gives you open subsets of an irreducible, and one can easily see that that's irreducible as well. Then now the definition. If you have a veil divisor, we say it's locally principal when what the name says. Like locally, it means that there is an open cover, that's the locally part, over which it is principal with the definition that we gave, principal being that on that neighborhood, it is the div of some f. I treat that u as my variety. I ignore the rest. And in that u, you have a f that is in C star of my u. So you can see u like this star, like a rational function in that u, and you take this, and you get your d restricted to u. So you have a cover where this happens. And not all divisors, not all veiled divisors do that. They are not all locally principal. Those who are, we call a Cartier divisor. And a principal divisor is locally principal because I can take the cover as the whole thing. A cover by one patch, that is the whole X itself. It satisfies the definition. So div Fs are Cartier for all of these guys. One can see that sum or difference of Cartier divisors is again Cartier, and that any veiled divisor that is linearly equivalent to a Cartier divisor is Cartier. Yes, because you would have a veiled divisor that minus a Cartier equals to a div that is also Cartier, so this one is okay and this one is okay, and you pass to the other side, this veiled divisor would be the sum of two Cartier ones, so it's Cartier. Very good. So then the claim over here was that the divisor that you get out of the polytope is locally principal. I'll keep it over there in the notes. Maybe let's not go too carefully over the proof, but I can just at least tell you, because sometimes it's just at least good to know how deep a result is. And this one is not deep at all. I'll just outline what computation one needs to do. What one checks is you need to check that it's locally principal. So then this is what happens. Here you have the polytope, and in your polytope you have some vertices. Those vertices correspond to the maximal cones in the normal fan. And each of those gives you an affine open patch in the variety. And by the way that the orbits are included, that's a cover. If I take, for example, the open patches corresponding to the rays, I don't get the whole variety. I'm missing some stuff. But if I take the open patches corresponding to the maximal cones, I get the whole thing. Then we work over those and show that it is principal there. And principal generated by what? One checks this, is direct. If you call this vertex M, which lives in M, over the corresponding, so then there is a sigma corresponding to that M. So there is a V sub sigma. One checks that in V sub sigma, one has, let me write the relation over here on this side. Over here I can write that over our D restricted to V sub sigma is just the div of this chi to the M over there. This, again, let me write restricted to V sub sigma. So it is principal. That's how the proof goes. And you will say, okay, and that this is equal to this is hard to check? Not, actually, it is built to make this happen. If you see, like, if the definition seemed weird at first, it's chosen to make this happen. And one just does the computation, the divisor was created so that this exact thing happens. So that when you look over the patch, it's like doing the div of the vertices, the div of chi to the vertices. Oops. Anyway, that gives you the idea of how this proof works. We have a cover of the variety by the open affines associated to the vertices, and in each of those, the divisor d sub p comes simply from div of the corresponding function chi to the m. Very good. So now, again, why do we care about these things? We will see in a second what these divisors give us. People define this object that is a vector space called the global sections of your divisor. It is the functions that essentially have like poles and zeros, like bounded by the divisor. It's the rational functions, non-zero rational functions, that when I do div of your rational function, and I add this, I get no poles at all. Like this greater or equal than 0 means coefficient by coefficient. Because what is this type of object? This object is like 7 times this subvariety, minus 20 times this other subvariety, plus 25 times that one over there. What we are saying is those numbers that I said, with some of them negative, are not negative. I mean, we are requiring that we put an F in this set if that happens. And as always, there is like union 0 here. Yeah. Okay? I mean, I want a vector space over here. Okay? And I mean, 0 doesn't satisfy this definition, so I just add it on the side. Very good. So it is the functions that do this. It's a very common thing that one uses when dealing with algebraic varieties, and one does this for Veil divisors and Cartier divisors. One can give this definition. When you have a Cartier divisor, it turns out that this one is an invert. If you let the u vary and do the same, this instead of xp, write an u and take the same definition, that gives you something called an invertible sheaf, but we are not going to need that during these lectures. We are going to just deal with this presentation of the Cartier divisor. And as I said, this inequality means that coefficient by coefficient, those are greater or equal than 0. People call that an effective divisor. And the functions that appear here are determined by the polytope. We are going to see how in a second. This is the claim. If you look at these global sections, is the name of global is because it's xp, and I didn't write a u but wrote xp. In general, if I write a u, and one would say the sections of that divisor, the global ones I can see like this. What is this saying over there? Yes, I have a divisor D coming from a polytope P. And then I ask, which rational functions f are sections of the divisor? No problem. You look at your polytope. You look at the set of lattice points. These guys, and possibly a couple more inside. I don't know, like let me write something crazy like this. Let's suppose that those are the lattice points. So what this is saying is that I have a basis as vector space for this one up here. I have a basis as vector space for that one, that are these guys. If these guys are like u sub 1, u sub 2, u sub 3, so on, after u sub r, the basis as vector space for the space of sections that I drew again up here is chi to the u1, chi to the u2, up to chi to the ur. For example, in particular, the dimension of this vector space of global sections is finite, and not just that, equal to the number of lattice points here, because I have a correspondence between those lattice points and a basis of this vector space. For the argument, the point is, I can just outline very quickly, say one word. What do you need to check? Well, first one uses that this one is invariant to realize that first, one can see that they are regular over the torus, so those f's have to be in C of M. And then after that, one uses the invariance to check that when a sum of some chi to the u's with coefficients is in there, each of the chi to the u's individually was there. And then after that, one just checks which chi to the u's satisfy the inequality. That becomes this sum greater or equal than 0. So that becomes, let me write it with some color. That becomes looking at this guy plus this guy greater or equal than 0. That becomes this thing. And you see, oh, that's for free from the polytope. And I really guess that that's why you define the polytope like that. The polytope is defined so that the points like this, like everything inside, are just computing the sections of the divisor. The inequalities defining the polytope, or defining the divisor, the way to define the divisor if you like, is so that this happens, so that this result holds. The chi to the u's in here are exactly the ones that force, that give you sections of the divisor. But what is that for anyway? So this property of ampleness, we can use divisors in algebraic geometry, commutative algebra, and other subjects. When we deal with variety, we use divisors to produce maps to projective space. What do? This is the idea. Like each of these points gives you a function chi to the u on the variety. Just use those as the coordinates to map to projective space. And it works, and if it came from a polytope, it will be nice, as we will see in a second. So this is our situation. We use divisors to get maps to projective space. In particular, for this divisor that goes from a polytope, we use rational functions from here, which we have just identified. We said that it's just the chi to the u's, or chi to the m's, if you like to call it m, that are inside the polytope. M are the lattice points inside the polytope. So let's make this concrete. Take Zn. Our original lattice n is Zn. Our dual lattice is again Zn. Each integral point in there, each integral point gives you a concrete function that looks like T1 to the M1, T2 product with T2 to the M2, and so on, in the torus. If I call T1, T2 to Tm the coordinates. But we are abbreviating that as a T to the M. But remember, this T has n entries, and this M also has n entries. So this notation that we used before is like T1 to the first entry times T2 to the second entry, and so on. Use those as the coordinates to map to projective space. So let's say one word again about the procedure. What are we doing? We start from a polytope. That polytope has some lattice points, M1 to M sub L in the notation that we're using over here. Each one of those gives you concretely this over here. Like the variables T1 to Tn, write the components of each of those points mi's. Just define a map phi that goes from your torus, C star to the n, to projective space of the size L minus 1 if there were L of these points, and the coordinates, it would go like T sub 1 to T sub 2 to T sub n. We are calling that T. This is sent to, if, for example, M1 had some entries, it would be T1 to the M11 product Tn to the M1n, and so on. Let me color something over here. Let me color something. This first entry, this is just the first entry of the map, came from this guy. The other mi's give you the other entries. Now some observations about that map that we defined over there. If you take nu, a positive integer, and you scale your polytope, as we said before, the normal fan stays the same, the toric variety stays the same. But the toric variety stays the same, but the associated divisor got scaled, and got scaled, because you see when you scale it, those AFs, the minus AFs, got scaled by the same number. So the divisor that simply has as coefficients, the AFs got scaled by the same number. Then this is what happens over here. Let the number in the front of your divisor grow, because you have now more of these chi to the u's. So you have more hope of finding chi to the u's that are non-zero at points of your variety. Because to get a map to projective space, let me go back. I would be in trouble if I have a point where all of these were to vanish, because this is on the torus. I am fine on the torus. But if I go out of the torus, if I want to evaluate those guys on my whole toric variety, I may have some trouble. I may have points where all of these guys are 0. But if I go and get more and more sections by enlarging my polytope, what this is going to say is the following. If you let your number that you scale your divisor by, so for example, 70 times your divisor, 200 times your divisor, one can prove that that map is a closed embedding, meaning it gives you an isomorphism to the image, and that image is a closed variety of projective space. So we use these ample divisors. We use divisors to get mapped to projective space. We use ample divisors to, after a multiple, get an actual embedding of your variety in projective space. And what we are saying over here is that if you take a polytope, that one might not give you an embedding in projective space, but just scale it. If you make your polytope larger, we can even say how much. Scaling it by n-1 always works. If you scale it by n-1, maybe it already gave you an embedding, but worst case, scale it by n-1, produce the map like that. Just look at the lattice points and use that as the coordinates of your map. Out of this first one, I just got the first coordinate. The other ones would give you the other coordinate, like here. You use the m1 for the first coordinate, ml for the last coordinate. You get a map to projective space. Maybe it doesn't give you an embedding, but if you scale your polytope, it does. Scaling the polytope again does not change the normal fan, and does not change the toric variety. It changes the divisor you are using to construct the map, and it gets better in the sense that if I scale it enough, n-1 is enough, n-1 or more is enough, it now gives you an embedding. In particular, XP is a projective variety. We already said this, but now we are seeing how it works. We before said a fan, a toric variety coming from some fan is projective if and only if that fan comes from a polytope. We are seeing here why that was true. We said it before. Because if the fan comes from a polytope, this is how you can get an embedding in projective space, making your variety projective. And now we say here, finally, that while 4.4 does not give a projective variety, sorry, an embedding in general, it is known that it gives you an embedding in the following cases. XP is a toric surface. So if you have a toric variety of dimension 2 that comes from some polytope P, and you do this procedure, you are good. You don't need to scale any further. The map phi sub P that goes from your XP toric surface to projective space of some size is a closed embedding, meaning it gives you an isomorphism to the image, and that image is a closed variety. For toric surfaces, we are covered. If XP is smooth, it also works. Like you don't need to scale any further, it works. And in general, if we're calling n the dimension of the vector space where we work, and of your polytope, you just need to inflate this much. That's enough. So if you want for sure to get an embedding, even if your original one did, but you don't care about changing the size, this one for sure works. Very good. So then what was one of the main results that we have just seen? We understand which toric varieties are projective, are the ones whose fan comes from a polytope with this construction of the normal fan. What was that again? The normal fan was, okay, the polytope has some facets. Each facet is dimension n-1, so it has a well-defined perp direction. There are many vectors in that perp direction pointing both sides, But since the polytope is integral, we can intersect with the lattice and we get something over there. Everything is rational over there. We can pick the first lattice point along the inner direction. That one is well defined. We call those NF if the facet was F. And for each for each facet, for each face of the polytope, we get a cone. Those form the normal fan. And out of that, we get our variety. So now let me, yes, please.
It's a little vague, but is there another way to get a fan out of a polytope?
We mention at least one more. There may be many more. One more is this one of that we did a moment ago. Say that this is my original polytope sitting. Maybe to change the coloring scheme. This is the set of axes, and we say we had this guy over here, and we did, if that guy was our P, we did something that gave us some guy like this P0. So pretend that your starting one is P0. And what we can do is, for assuming that you can translate to put this polytope in, so the origin is inside, you can do this construction. It's like the fan over the faces of the polytope. You go face by face. So for example, for this one that I'm going to color in green, I get the cone spanned by each of these points. So it will look like, so it will be the first quadrant in this case. And out of that, one can show that what one gets is a fan. Very good, thank you for asking. So now we were mentioning, let's go back to some of what we have covered. Being affine, being like complete, or with the complex topology would be compact, and projectivity and smoothness. We have said some about those things. Yes, I'm sorry, if I have missed any of the questions, please, you can call me or something. Yes, please, you have a question?
Yeah, all of Cartier divisors appears in this way, or there are some missing Cartier divisors?
If Cartier divisors appear this way, I guess all divisors I guess this is the situation. What is the pathology that can occur? If you have, we have this one, and we have, let me try to choose something, say these three that already give something, and then let me do an additional one over here. So a divisor would be read off kind of like this. Put a coefficient A on this one, a coefficient B on this one. Let me put the orange last. A coefficient B on this one and a coefficient C on this one. And the coefficient D on this one. So what is happening? If I am looking at my polytope, the polytope is intersection of the half space corresponding to this, that is intersection minus A. Intersection like greater or equal than minus A. This one would be dot product with this direction, greater or equal than minus B, and so on, and this one greater or equal than minus C. So if I go to draw my polytope, say that this corresponds to the blue one. Maybe I can do some coloring scheme over here. Let me keep the blue ones for a second. And then say that my second one gave me I'm looking at the perps of these guys. So I am now looking at one, say like this, and I'm looking at one like this. Okay, so then this one came from dot product with the corresponding one is minus A, dot product with this one is minus B, and dot product with this one is minus C. So now, depending on the value of D, the perp might be in so many places. Might be here, might be over here, might be over here, might be over here. Then there is this issue that if I try to define the polytope, depending on the position of this 1D, I might not be able to read this at all, you see? So I can, in general, not go back. I have this issue that if the number D was such that I'm looking at this half space over here, then the polytope that I get, I can color it right now. I'm going to color it in green that you guys see as yellow, I believe. Right? This is green. Well, anyway. The point is that if you give me this polytope, I can tell you these coefficients for this guy, but not this guy. So maybe the correspondence is not perfect in that case. But when your polytope is the one coming from, like when the fan comes from the polytope, in that case you can go back and forth. Like in that case you can, yes, in the case of ample classes, one can see that there is a correspondence there. So this divisor would not be as good as the fan of this polytope is not this one, you notice. So if you just give me a polytope, I have a little bit of trouble over there recovering the divisor because of this that I told you, that polytope might not give you the fan. But if the polytope, when you take the normal fan, is exactly this one, then in that case, yes, your Cartier divisors, like you'll get this way. But if your polytope is not one that gives you the fan, you cannot read back all the coefficients. This is a concrete example where you couldn't. Very good. So going back here, what have we said during the past few days? We have said that I'm putting normal as part of the definition of a toric variety. We have learned that affine toric varieties all arise from a cone, as before. All toric varieties arise from a fan, as before. All projective toric varieties arise from a lattice polytope. I should even add that word here. Arise from a lattice polytope with this construction of the normal fan, which can also be seen like these are the duals. Like the cones that you get out of, say, each vertex are the duals of the maximal cones. Like you take dual, if this is sigma dual, you take dual again to get sigma. Every toric variety that is smooth, like I can characterize that. This is if and only if for each cone in your fan, you look at the first integral point along the rays of the cone, they are part of a z basis of the free z module Zn. That's how we characterize smoothness for toric varieties. And we characterize being complete, which again, if you use the complex topology, it will be compact. A toric variety has this property of being complete if and only if the fan is what is called complete, meaning the union of the cones covers your Rn. These things we have discussed, so I'm just summarizing. Then, for example, let's look, now that we have these characterizations and smoothness and all, one can, just some applications, one can start producing examples of what you need in your daily work. This is one that is very well known. Say that you want, just to show off, or maybe because we really need it for work, a smooth and complete, but not projective variety. We can already do it in dimension 3. So something that is smooth, complete, meaning like compact, and not projective. Many people know examples of these things, but one of the easiest examples perhaps to give will be using toric geometry. This one is from Fulton's book. Consider the toric variety. This picture is as misleading as it can be. So it's just a cartoon, and that's what it says over here. The labels are not the points, but is a point that gives you the ray that you need to use. This is telling you how the things fit together. So then, for example, the midpoint of these two would be E4 over 2, right? And the midpoint of these two is also E4 over 2. So how can it be that the midpoint of those two segments is the same? Just because this is a cartoon. It's just like, I mean, it's telling you how to fit things. It just means that you take the origin, and from there you are going to do the cones over what you see over here. So we are working in R3, take the three canonical vectors E1, E2, E3, define E4 as the sum of E1, E2, and E3. And then, for example, take the cone spanned by the vectors minus E1, E3 plus E4, which it would be E1 plus E2 plus 2 times E3, and minus E3. So that's one of your cones. This is just telling you how to get your fan. Okay. Then the claim is that this fan is smooth. That one is not bad to check at all. Let's take a look. The maximal cones give me open varieties that cover my toric variety. I don't need to take them all. Like if I use them all, yes, I get a cover, but there is some redundancy over there. If I only use the maximals, I already get an open cover. So if I want to check smoothness, I only need to check the maximal cones, giving me something smooth. And we can just see, like take any of these guys, for example, this one. Is that a smooth cone? Yes, because these three guys are a basis of Z3, right? Minus E2 and minus E3, if I subtract from here, I get, I can clear that E2, and then using minus E2 and minus E3, I can clear and get E1. So they generate E1, E2, and E3, so they generate the whole lattice. So these guys are a basis. Very good, and the same for the other ones. You can check it one by one, it just works. So it's very easy to verify. So it's indeed smooth. It is compact because we know that if we take any fan, that when we do the cones, they cover my R3, is complete, it's compact. Very good, so we get that one for free. Again, what are we saying in case maybe it's confusing? Please let me know if something is confusing. What we are doing is that we pretend the origin is inside when it is, and then what you do is you take the cones like this, the cone over these three. This is one of the cones. See, that one over there is one of the cones, like from the origin, the directions that you are going to see over this cone. Let me go back here for a second. The directions that you would see over this one. From the origin over that one, this is what we get. And they do that for every single triangle that you see in this subdivision of a tetrahedron. So this covers the whole R3. If I put those cones together, so we are somewhat in good shape up to now, smooth and complete. Why is it not projective? Maybe I cannot show it to you here, but I can just tell you one word. What you can check is that there are some inequalities that one can get out of this picture. And when you, for each of these, like the three big faces here, you can get a certain inequality, and then those close around to a contradiction. You can see, for example, in the book of Fulton, or we can talk about this. It's not so bad, but it's something that now one can do with convex geometry. One can now do a little bit of convex geometry to, I just don't want to say much more, but what one shows here is that the divisors that could give you an embedding to projective space here would have to be trivial, so you don't get an embedding. And that can be checked with a certain inequality. I mean, it's something well known in toric geometry. One knows what inequality you need to check. You produce that one in one phase, produce it in the other one, produce it in the other one, and add to a contradiction. Another way to think about this is that if you consider that fan, what is happening is that is not the fan over the faces of a polytope. So the following is what is not happening. Say that I am in R2, and you give me a fan looking like this. These are the rays. And then the cones are like these ones over here. Let me use some lighter color for those guys. So the cones are like this. This guy, and this guy, and this guy. So I can make this be the normal fan of something. I can just take like a perp here, a perp at any distance I like, a perp at any distance I like, a perp at any distance I like, and a perp at any distance I like, and take this as your P. That P has as normal fan the one that I started from, so it makes it projective. The point is that the claim that one can check with some convex geometry is I cannot do the same for the one in Fulton's book. So after one goes and checks it, this one is not, I mean, maybe I can do check mark. So it's not projective, one can check that. So you can use this theory of toric varieties to construct examples that may fit something that you need. Something more, then what is the fundamental principle of what we have been doing these days? That you start with some combinatorial data, very concrete, like finite in a certain sense because it's generated by finitely many vectors. So out of that, you produce a variety. The variety determines, say, if it is smooth or not, if it is complete or not, its projectivity. It determines the constructions that you get out of varieties, like homology, Chow groups, K-theory, covordism, and so on. Then this combinatorial data determines your variety, which determines all the constructions out of the variety. Then the combinatorial data determines all of those constructions. So then what people have started to do is, okay, let me describe each of those things. So you have, as we just saw, a description of smoothness in terms of the fan, description of completeness in terms of the fan, description of projectivity in terms of the fan, but also of homology, Chow groups, K-theory, covordism, all of these are very well understood. All properties of algebraic varieties should admit a combinatorial interpretation for toric varieties. That's the fundamental principle here. For example, there is this fundamental construction in algebraic geometry that allows you to resolve singularities. It's called a blow-up. It is defined by a certain universal property. You take some, in general, it's like a closed-off scheme, but let me say a subvariety, and you replace it by a Cartier divisor, and it is done in a universal way. Like if you have a map where the subvariety that you started from, there is a way to take an image over there. If it becomes locally principal, then it factors to the blow-up. It's some construction defined by a universal property, resolves singularities. Then, for example, if you start from affine space 2 and blow up a point, you might have seen this picture, you get a Cartier divisor instead of that point, and everything else is the same. If downstairs you remove the point, and upstairs you remove the Cartier divisor that you just put there, they are isomorphic. Turns out that in toric geometry, some blow-ups, when you blow up invariant things, they become, they can be dealt with the toric data. It's basically some type of subdivision of your fan. There are some rules that one needs to follow, but essentially subdivision of your fan. So let me just give one example over here. If you start with P1 cross P1, and you fix a point, let's pretend that we are here inside P3. There is a way to put P1 cross P1 as in P3. So let's put it over there, and then from a point, let's project down to some P2 somewhere over there. If we project down, so where does every point go? If you give me a point over here, and I have a P2 over here, a linear P2 embedded, all of this inside P3, well, I got something somewhat well defined. I use a line over here. Luckily, I can cheat over here and put the point in, like if I didn't miss. And then I get a projection point here, a unique intersection point of this linear thing with this other linear thing, because the intersection with multiplicities should add up to 1. So I get a 1 point here. So I'm in good shape. But I don't know where to send the point A that I started from. So I'm in trouble. I can define it elsewhere, but not at the point that I'm projecting from. Okay. What if I want to go backwards? Because this feels like if I am hitting all different points, right? I am hitting everywhere, but I cannot go backwards, you see? Because this is a P1 cross P1, so it has this line over here. I mean, in the presentation that I'm giving, one can see the actual lines over there. And all of these guys go to the same point. So I am in trouble over there. But what happens, our reference is the book of Gathman, and this is a somewhat standard exercise that one solves in an algebraic geometry class, is that if I blow up this point, I resolve the map, so I have a map down now. Like on P1 cross P1, I cannot define the morphism in the whole P1 cross P1. But if I blow up that point, replacing it by a copy, or I mean, like what that one is, I guess this is smooth. So you give me a P1 over there. That would be what you call the exceptional divisor. Now, turns out that one can define the map in that new object. And it turns out that if one goes backwards, blow up this point that doesn't know where to go, and when you blow it up, you'll get a copy of P1. And if you blow up the other one on the other side, let me do it with orange, the one coming from over here, it gives you another bad point over here. If you blow up that one, and you produce yourself another copy of P1, now these guys know where to go. These guys go to all of these guys, and these guys go to all of these guys. So the claim is that one can define the map backwards. This can be made into a rigorous argument. A reference is the book of Algebraic Geometry by Gathman, which is free online. He writes this as the intuition, and then writes down the algebra. But if a person, and I gave it to my students, for example, in the algebraic geometry class, and then they produce the solution. But if those guys do toric geometry, one can see that, I mean, this is the picture first. This is what happens. This is the picture that Gathman has in his book, that you blow up here and here and here in the one above, and now you have birational maps both ways, that you can see that, and they compose to the identity in some open. In both directions, it means that they are isomorphic. So then the claim is that this happens. These are isomorphic. P1 plus P1 blown up at a point is P2 blown up at 2 points. And then again, Gathman writes down the nice proof, and then maybe students write down as well, but with toric geometry, you could do a rigorous proof also like this. This is what is happening. So you start from your P2, this is first a cartoon before we do the proof. In P2, you blow up a point. So I just colored it so that you see that this blue point becomes this copy of P1, and this red one now went over here. You blow up now this green point. That green one becomes a copy of P1, and the red one now is over here. And then you cannot contract every curve that you see around, but one checks, and this one can be contracted. It has like negative, it has like self-intersection -1, and then there is some criteria for that. You can contract that one, and one checks that you get, I mean, the cartoon is saying that the claim is that you get P1 cross P1, but now this is the point. This picture is all toric. So this guy is this guy. Like the first blow up over there, I need to get better at using Luis's iPad. Then the first blow up is just subdivision along this point. So subdivide and you get this one. The next blow up is exactly subdivision along this point. So you get this fan. And this blow down, meaning the inverse of a blow up, would be just contracting one of those guys, contracting this one. Look, so that guy disappears. It's like the blow up but done backwards. This thing here is actually not like this one. This is a cartoon. This is a rigorous argument. The first one is P2, rigorous. And this one, up to a change of coordinates, you see is P1 cross P1. So this would be a completely rigorous solution of the one that I told you a moment ago. So this is one more example of how you can use these combinatorics to do stuff about algebraic geometry and construct examples of whatever you are computing in your work. And I think this is a great moment to stop. I would like to thank you all for your attention. And thank you. You too. Thank you.
Thank you very much. Are there any questions, Jose?
Yes, please.
Yes. What's the condition for smoothness in the polytope?
Yes, so what happens is that one of these smooth cones looks, let me just try to use thank you, I mentioned, thank you. One of these smooth cones, so they look as follows. Up to a change, let me take a maximal one. You see it say in situ. So if I take one of these maximal ones and it's smooth, I can change coordinates. And up to a change of coordinates is just like if I had the first, in R2 it would be like the first quadrant. In R3 it would be like the first octant. You see, like if I have a maximal one that is smooth, the rays give me first lattice vectors that are a basis of the lattice. So then I have a matrix with integral entries and determinant 1 or -1 that makes those into the canonical vectors. So if you have a smooth one, you really have this guy over here. And then let's see what the dual is. The dual of that guy is smooth again, is itself. So then to answer your question, in the polytope, one can see that when you constructed the normal fan, it arises this way. There is a cover of your variety if you only look at the vertices, because the vertices here give you the maximal cones on the other side. So if I, for example, take one of these guys, the cone is the dual of the directions I see here. And I want the one over there to be smooth, but this one is the dual. And the dual of smooth like this is smooth. So what I'm saying is that this one be smooth. So I can read here as well. So that's the condition. Look at the vertices and look at the cones out of each of those vertices. It's a smooth cone, like translate this picture so that it sits at, that one is the origin. And look at whether this cone that you see from that vertex is a smooth cone in the sense that the very first lattice points over there are part of a basis. In this case, if it is a basis of Zn. You can read it in the polytope. It's the answer, and in the same way as you read it in the fan over there. And you could also read it on the NFs. Yes. It's equivalent because we just said that smooth, the dual, this is smooth here. The NFs is reading it in this one, and these first generators here is reading it in this one, which is the same. Yes.
Other questions? Okay, so I have a couple of announcements, so please wait a little bit. But before that, I want to thank you, Jose, for all this very nice and interesting course that he kindly gave us. So I personally must say I've listened to several courses on Toric Varieties and Toric Geometry, but this is one of my favorite ones. I think you were really clear, and you give a lot of intuition, and you did some non-standard things also. So thank you very much, Jose.
Thanks, I appreciate your kind words. Thank you.